Our first speaker and first group is Jihyun Oh. So could you start your presentation and introduce a little about yourself?
Yeah, Professor Lee, can I deal with my screen?
So here is, so who is sharing the screen right now?
Oh, I'm sharing the screen right now.
Yeah, so in your presentation, you are going to tell Dongyuan next slide. So when you want to
Okay,
move forward, so he will turn the slides for you. Yeah, we will not
okay,
switch screen sharing back and forth to save some technical issues.
okay. Hi, my name is Jihyun Oh. I'm a second-year doctoral student in social welfare. Um, yeah, let me get started. So today I want to talk about the topic, which is review of odds ratio versus prevalence ratio in the cross-sectional studies on binary outcome, which one is better? The reason why I chose this topic is that previously I heard from one of my friends in public health that there is a rule which is if the binary outcomes prevalence is greater than 10%, a Poisson model should be used instead of a logistic model in that field of the study. So based on my understanding, the rule for model selection sounds strange to me at the time. So through this class presentation and survey paper, I wanted to clarify this point. So yes.
Yes, okay.
Thank you. So this is my outline. First, I will briefly explain some background about this topic. And the second and third, I will explain the concept of a prevalence of the binary outcome and its relationship with the estimation precision. First, I will briefly review Martinez et al.'s 2017 study to explain why we should support prevalence ratio generated by other alternative models instead of odds ratio generated by conventional logistic regression model when the prevalence of the outcome is high. So also I will summarize the study key points conducted by Martinez and colleagues in terms of a Bayesian model, equations, and the simulation results regarding which model is better, a logistic model versus other four models. So please move on next slide. Thank you. So estimating the probability of a presence of the outcome, such as poverty, deprivation, and depression, or the risk of having a certain disease, heart attack, or obesity, and pain is key, as you know, in the social science, including social welfare and the sociology and etc. And public health, including epidemiology and medicine and veterinary medicine literature. So most of the outcomes used in social science and public health literature are not continuous. That is, those outcomes are binary or categorical variables. So as you know, typically for binary outcomes, logistic model is applied, as you know, whereas for count outcomes, Poisson model is applied. However, as I mentioned before, some scholars argue that odds ratio by logistic model is less efficient than prevalence ratio by Poisson model in terms of precision of the point estimates, that is effect size. So why? So yeah, thank you. So then in this slide, I will explain three measures of a binary outcome. First, as you know, prevalence or probability, it means that the number of subjects, such as with negative health outcome divided by the number of subjects in total. Meanwhile, odds means that the number of subjects with a negative health outcome divided by the number of subjects without negative health outcome. And odds ratio is defined as the ratio between the odds. So then what is the relationship between prevalence and odds? As you can see in the table, depending on the number of people with, for example, heart disease among 10 people, the prevalence and odds are computed. The key point is that, like the first row, the prevalence of the outcome is similar to odds when prevalence is rare. However, the prevalence increases, the prevalence, the difference between the prevalence and the odds increases. So this is why we should consider some potential biases that may derive from the relatively high prevalence of the outcome in estimating betas, that is, effects and their confidence intervals. So, do you want? Yeah. So, to precisely measure the association between exposure X and health outcome Y, the prevalence of the outcomes such as disease is crucial, as you know. So to detect high prevalence, the benchmark is 10%, which is suggested by public health literature, including Martinez et al. 2017 piece, which I will discuss in the next slide. So if the binary outcome is rare, that is the prevalence is less than or equal to 10%, odds ratio generated by logistic model is satisfactory. So this means that odds ratio is a good approximation of a prevalence ratio, as we saw in the previous slide. However, the binary outcome is not rare, that is common. The prevalence is greater than 10%. Odds ratio generated by logistic model is not satisfactory. It means that odds ratio is not a good approximation of a prevalence ratio, because odds ratio tends to be overestimated or underestimated, and its 95 confidence interval tends to be wider. So the risk or probability of having the negative health outcome estimated may be biased. So to resolve the issue of imprecision of the odds ratio estimates by logistic model, when the prevalence is high, as I mentioned, greater than 10%. So alternative models such as Poisson with robust variance, and log binomial and Bayesian log binomial model can be applied. Don't you want? Yeah, please. Yeah. So in this slide, I will briefly summarize Martinez et al. 2017 study that addressed the issue of the imprecision in the effect size and the confidence intervals using logistic model rather than Poisson model when the prevalence is high or greater than 10%. So Martinez et al.'s 2017 study aims to examine how alternative models can yield better estimates compared with the logistic model. this article comes from the veterinary medicine literature. So they use the data based on 388 herds randomly selected from about 80,000 dairy herds in southern Brazil. So the outcome is antibodies against the bovine viral diarrhea virus called BVDV. So key finding is that based on meta-analysis, most of cross-sectional with binary outcome in veterinary medicine were with misinterpretation of odds ratio and the prevalence ratio. This is because most of scholars in this area are confused like me, these two concepts, odds ratio and prevalence ratio. So based on simulation analysis, logistic model overestimated the effect size and made their confidence intervals wider compared with 4 alternative models, as I mentioned, Poisson, robust Poisson, Poisson with robust variance, and a log binomial and Bayesian log binomial model. So the study's findings suggest that a logistic regression model should not be used when the prevalence of binary outcome is high, greater than 10%. Please, next, yeah. So Martinez and colleagues explained the Bayesian model equation between a logistic model as a conventional approach to binary outcome and other models such as Poisson and the log binomial. As you can see, the first equation means a logistic regression model. In the left hand side, there is a logit as a link function that is log of us. And in the right hand side, there are delta sub 0 as an intercept and the 3 independent variables in their model. And compared with the first equation, second and third equation use the log as a link function. So Martinez and the colleagues suggested that Poisson and the log binomial models are better to use instead of a logistic model when prevalence is high. So in their study, the prevalence of antibodies against the bovine viral diarrhea virus code, as I mentioned, was 24%. Yeah, so could you move? Yeah. So their main results can be summarized using this table. So as I mentioned before, the outcome variable is the prevalence of antibodies against bovine viral diarrhea virus code, the BVDV. So 3 independent variables are routine use of rectal examination and the direct contact over the fence and farms that do not use artificial insemination. So as you can see, the first column refers the conventional approach to a binary outcome, that is logistic regression model, including the estimate and 95 confidence intervals for 3 independent variables. So from the second and the fifth column, the estimates and the 95 confidence intervals are presented as alternative models. And then the remaining last 3 columns, relative changes in the effect sizes by comparing between each model and the referent log binomial are presented. So the log binomial model was used as a reference model because the estimate generated by log binomial model would be the second best and can exist in reality. So the key point is that for 3 independent variables, their effect size, as you can see, and the confidence interval are greatest logistic model, indicated in that logistic model performs worse compared with 4 alternative models. So the results suggest that odds ratio, coefficient, and their confidence interval are overestimated. So for example, regarding the effect size of the first independent variable, as you can see, 69.91% means that compared with the referent log binomial model, the effect size generated by a logistic model increased by 69%, which indicates overestimation. So that's it.
Thanks, thanks, Jimmy.
Yeah.
So I would say I don't buy this article at all. I think the argument is not convincing at all because these models are estimating different parameters or they have different parameters. So you cannot really compare the estimates or confidence intervals of different parameters. So comparing the confidence interval here, this table itself is not really valid. So I actually don't know what they're talking about. So that's just my point, but you can still write your survey paper. You can still summarize their key points, but I just want to say that it's not convincing to me. I don't really think that the comparison is meaningful. And also if you go back to the previous slide where you define the odds and the prevalence, yeah, just go back to Dongyan, further back. Yeah, exactly here. So that table. So I want to point out that, so Dongyan, can you go back two more slides further? Go further, yeah, here. So I want to say that, no, the table where she has the prevalence, odds, that table, yes. So here you are confusing yourself between what odds and odds ratio. To me, you see, what you write in the table is the odds ratio. But you define the odds already as the ratio. You see, in the second item, the odds is defined as the number of subjects divided by the number of subjects with negative health and number of subjects with negative, sorry, I think you repeat yourself. You have the negative health outcome in the numerator and denominator. So what I mean is that I think that's just the odds ratio. What else? So why do you need to define odds and odds ratio separately?
I
guess this is odds.
Yeah, this is odds.
Oh, really?
I think you just need prevalence and odds, or you can call them prevalence ratio or odds ratio, but I think that's just the terminology. You don't need both odds and odds ratio.
Sorry, Jessica. I guess odds ratio and odds are not the same based on my epidemiology courses. But I do agree with you, like we all know prevalence and odds, they are not the same thing. Yeah.
They're not the same thing, yeah. But if you look at that, so in logistic regression, think about what we talk as the systematic structure in our class. In logistic regression, you are assuming the log of raw. Let me just use the terminology in your table. You're assuming the log of odds is the linear function of the predictors. That's our systematic structure. In Poisson regression, you're assuming log of prevalence, log P, is the linear function. So therefore, the two linear function and their betas are not directly comparable. They're not the same thing.
Okay, I will check. Yeah.
You should check this because I remember in my epidemiology course, I think the first course is that teach you prevalence and odds. They are two different concepts. So I don't think they are comparable to each other.
Okay, I will check the notation.
Responses. It's no wonder that your coefficient estimates would differ.
Okay, I will check, Professor Lee.
Just argue which one is better based on the different parameter estimates will definitely give you different confidence intervals. But if the parameters are different, then comparing the confidence intervals is not meaningful. So what should be done probably is the goodness of fit to data. You can talk about that.
Okay. Okay, thank you. Yeah, I will check.
So, so let's move on to our second presentation. Thank you. Thank you for the presentation.
Yeah.
Thank you.
Thank you.
Yeah, so our second presenters are Yik Lun and Deqian, I think.
Yeah, please start.
Hi.
Hi.
Hi, I'm Deqian Kong. Today our survey topic is related to the ERGAN model, which is exponential family random graph model. Next slide, please. Thank you. Let's first look into the networks. Networks are a form of relational data, often represented as a set of pairs of individuals called nodes, where each pair can be directed or undirected, and this pair is called an edge. For example, we can regard this network as a disease contact network, where the nodes are individuals and the edges indicate some type of physical contact or social distance. Or we can also regard this network as a friendship network, where the nodes are two students and each edge indicates that one student considers another student to be a friend. We can visualize the network by as relational graph in the lab. In practice, we also use n by n dimensional adjacent matrix to represent a network. Next slide, please. Next, I will give a brief introduction to the general framework for the random graph model. Suppose we have defined the fixed node set. We assume that each edge is a random variable, and the random variable equals one if there is a relationship between two individuals. In this way, we have total n choose two random variables, and we can form 2 to the power of n choose 2 random graphs. Then we need to specify the dependence assumptions among the random variables. For instance, if all the random variables are independent, the simplest model for this graph is Bernoulli random graph, in the sense that each edge follows a Bernoulli distribution. Since too much random variables would produce too many parameters, which is obviously not a good thing. So we can simplify the model based on the homogeneity of the edges, or other we have predefined constraints. Finally, we can estimate the parameters by MLE. Next slide, please. Okay, thank you. After the introduction of the random graph, the formulation of the exponential random graph model, the ERGAN model, is very obvious. Here, we define the ERGAN model if the probability of the graph follows an exponential family distribution, as what we have learned in the class. Here, the K of eta is the normalizing constant, which is hard to compute, where the eta is the parameters we are interested in. G of Y is the observed statistics of the network, such as the number of the edges, the number of stars, or the number of triangles, and so on. Next slide, please. Thank you. Here we can write the log likelihood function as L of eta as this. The psi of eta is the log of the normalizing constant in the previous slide. In the following, It's just the optimization process of the MLE using gradient descent. Only one thing here I need to point out is that this score function or the gradient of this normalizing constant is the expectation of the network statistics. And this score function makes sense because the gradient is calculated by the difference between the observed statistics and the expected network statistics. The problem is that this expectation is hard to compute. We have to use MCMC, Markov chain Monte Carlo, to sample the different networks and compute the expectation. All right. Next, Alan will explain the process of MCMC and the other optimization process.
Hi, everyone. Yeah, so now I'll talk about how to use Metropolis algorithm to draw MCMC sample from the target distribution. So in a binary network, a diet can either change from 0 to 1 or from 1 to 0. So now let's denote that delta G for the IJ pair as the difference between the two network statistics. And one is that when Yij equal to 1 and rest of the network stay the same. And the other is when the Yij equal to 0 and rest of the network stay the same. So in this design, that the acceptance ratio for the new proposal value will be equal to pi, where pi is the difference of the probability of the new value over the probability of the old value. And specifically for our case in our binary network, the acceptance ratio change from for diet change from 0 to 1 will be the exponential of the eta multiplied by the delta G. And then the acceptance ratio for a diet change from 1 to 0 will be the expectation of the negative eta multiplied by delta G. Next slide, please. Yeah. And also, it is also computationally expensive to generate MCMC sample at each iteration of the parameter update. So instead, we use the log likelihood ratio as our new objective function. So first, let's denote that eta j to be the parameter of another ergon. Then the ratio of the two normalizing constant can be estimated by this, which is the expectation of the exponential of the difference of the parameter multiplied by the network statistic. And then we can further estimate this, this quantity using Monte Carlo integration, where the Y1 and Ym is the MCMC sample drawn from the target distribution, which is parameterized by the eta 0. So yeah, with the ratio approximated, and then we can now rewrite our approximate log likelihood ratio, which is the difference of the two log likelihood, and then which can be further expanded as the difference of the parameter multiplied by the observed statistic, and then minus the difference of the approximate normalizing constant ratio. So that we can just optimize this objective function, and then the maximizer will give us the estimate of the parameter. However, there's another ratio. There's another problem by using this method. The log likelihood ratio degrades quickly as eta moves away from eta 0, so that there are two alternations are made to improve the parameter estimation. Yeah, the first one is called the loose distributional assumption. Since Y1 to Ym is MCMC sample drawn from the target distribution, we can assume that their network statistic multiplied by the constant, which is the difference of the parameter, follow a normal distribution with this mean and this sigma square. And then M0 and then the sigma 0 is the mean vector and the covariance vector of the MCMC sample. And below, we also draw a random Southern network here, and then they appears to be follows a normal distribution approximately. Yeah. The second improvement on the parameter estimation is called a bridge sampler. So the basic idea is that we constrain the maximum amount of the update on the parameter to prevent the degradation of the log likelihood ratio. So the idea is that we create a pseudo observation between the observed statistic and our current estimation. So in this graph, we have the parameter space, which is the first line, and then we also have the sample space, which is the second line. So that before the eta is updated based on the difference of this xi bar and the network observed statistic. So by using the bridge sampler, the estimator eta is updated based on the difference between the xi bar and the xi hat, which is the difference between our current estimate and our pseudo observation. So in this way, we can constrain the maximum amount of update on the eta on the parameter space And then we can also preserve the accuracy of the log likelihood ratio. Yeah, so putting everything all together, we have the basic algorithm that is used in the library ergom in R. So first of all, at the iteration t equals 0, we initialize the parameter eta 0. And then we generate MCMC sample from this target distribution, which is parameterized by eta 0 at the first iteration. And then we calculate the current estimate of the network sample. And then we define our pseudo observation, which is a value or observation in between the observed statistic and our current estimate. And then we find the maximizer of the log likelihood ratio that is with our loose distributional assumption. And then we repeat this process until the parameter converge. And because of the loose distributional assumption that we define with the normality assumption, in the step 4 for the optimization for the objective function, we have a closed form solution for our maximizer. Yeah. So to conclude our presentation, we use an experiment as a quick demo. So here we have two network statistics to fit the ergom. One is the total edge of the network, and the other is the number of pair for ij and ji both exist. So here we choose, we just use a very simple tutorial data set here, the sample-like data set. So for these two, there are total 88 edges and then 28 pair of the mutual connection. And then here is just a brief summary for the output. So the top is the summary is the output from the library ergom, and then the other is and then the bottom is our calculation from the algorithm that we just described before. Yeah, and then they return about the same estimation. Yeah. So this will conclude our presentation. Thank you very much.
Thank you very much. So I just have two questions. So first of all, in what applications do you have network data with just the total number of edges and the number of pairs that are mutually bidirectional, without having access to the actual adjacency matrix? That's my first question.
Do you mean like why we choose these two network statistic, or?
Oh no, I mean, I should say, under what case do you want to fit this ergom ERGM model? Yeah, that's my first question.
Mm-hmm. Yeah, so for this ergom, we are specifically tracing or looking at the network statistic. So the network can vary in different ways, but they may produce the same network statistic. And also, yeah, for our demo, we just use a very simple, maybe in practice, we don't use this kind of simple statistic, but in this presentation, we're just trying to show that the feasibility of calculating that. But yeah, in practice, maybe we will use more difficult network statistic.
I guess my question is that network statistics can be directly computed from a given network, right? That's the fact. You can compute a statistic. Then what are you estimating? You're estimating the parameters, the canonical parameters in an exponential family distribution. But what does that parameter mean? What can you learn from that estimation? That's my question. If you estimate the eta, then what would you do next?
I think we treat the observed network is just a realization.
Yeah.
So we are trying to estimate the underlying parameters. This underlying parameters of the network can produce the realization, some different realizations, different kinds of networks, but produce the same network statistics.
But I just want to say that in this exponential density form, the eta is a parameter, but it's quite abstract, right? In practice, once you fit the parameter, essentially you fit the model, you fit the model. What would you do with the model? What's next? What's the application potential here?
For example, we treat the network statistics as the stars of triangles of the network, right? We can fit the model. We can get the parameters for different, like 3 triangles, 4 triangles like this.
What's the meaning? What's the meaning of the parameter? Just like in our linear model, we know the meaning of beta. That's the effect size. What's the meaning of eta here? Given the net per statistics you described, like the number of triangles. Okay, you can think about this question. You don't have to answer it for now, but you can think about this question. But I think this is very important to address the usefulness of the model. You don't fit a model just for the model's sake. You want the fitness, you want the estimation to be meaningful in applications.
Sure,
Okay.
yeah, we can look into that and then describe more application and the explanation for the parameter in our paper.
Exactly.
Mm-hmm. Yeah.
And also, I think for that, the pseudo observation, I think that should be pronounced as Kasai. It's not, I think you pronounce as Zai, and it was quite difficult for me to figure out which notation it refers to. I think it should be pronounced as Kasai.
Oh, okay. Mm-hmm.
Okay.
Thanks.
Thank you. So let's move on to our third presentation.
Yeah, sure. So our third presenter will be Nathan.
Hello.
Hello.
So go ahead and start.
Yes, please start.
Okay. Hi, everybody. My name is Nathan Hoffmann. I'm a third-year PhD student in sociology. And my project is on Bayesian model evaluation using leave one out cross-validation and WAIC. Next. Thanks. A question I guess we've had throughout this course and we addressed in the last lecture is how to estimate the accuracy of our model. And there are sort of two big methods out there, cross-validation and information criteria. And my presentation asks how are information criteria and cross-validation linked? And in a Bayesian framework, we can show that WAIC, which is related to the AIC, and leave one out cross-validation are nearly equivalent. Next, please. So just giving some notation and definitions. Suppose we have data y1 to yn modeled as independent given parameters theta. And we have the likelihood, p of y given theta. We have a prior, p of theta. Posterior, p of theta given y, which is proportional to the product of the likelihood and the prior. And then we can also calculate the posterior predictive distribution, p of y tilde given y. So y tilde is new data. And it's simply the product of the likelihood of the new data times the posterior marginalized over the parameters. And then we can use Markov chain Monte Carlo methods, MCMC, to obtain samples of posterior and posterior predictive distributions. And later on, I'll show an example where we use Hamiltonian Monte Carlo using Stan. Next, please. So our goal is to estimate the out-of-sample point-wise predictive accuracy, which is closely related to the Kullback-Leibler or KL divergence. Ideally, we would like to estimate the ELPPD, expected log point-wise predictive density for a new data set, given by this formula here, where PT of y tilde I is the true unknown data generating process for yi tilde. But it's unknown, so the best we can do is try to estimate it. The model with the highest ELPPD will have the lowest Kullback-Leibler information and hence the highest posterior probability. This value is basically always negative, but we can get it less negative. The goal is to get it less negative, and it implies that we can get better accuracy in prediction out of sample. Next, please. Another useful quantity is the LPPD, which is a log point-wise predictive density, given by this formula here. And in a frequentist perspective, this would simply be the log likelihood. But in a Bayesian framework, we need to compute this over the entire posterior distribution. And we do this by using MCMC draws of the posterior parameters, theta s, for s draws. And this gives us the computed log point-wise predictive density. So in this, we sum up the likelihood for each of the parameters drawn from the posterior, take the mean of that, take the log of that, and then sum up over all the observations in our sample. This is an overestimate, however, the ELPPD for future data. It's an overestimate, meaning it's less negative. It's a little too optimistic about our predictive accuracy. Next, please. So one way to estimate the predictive accuracy is cross-validation, testing the accuracy of the model out of sample. If we use the maximum number of folds in cross-validation, this gives us leave one out cross-validation, which is given by this formula here. So the P of yi given y minus I signifies the predictive distribution given the posterior fit to the data from leaving out observation I. But this can take a very long time to compute because we have to fit the model as n times for n points that are left out. Next. If the endpoints, however, are conditionally independent in the model, then we can use importance ratios to evaluate the Liu predictive density with draws of theta s from the full posterior density. And RIS here is the importance ratio. And you can see that the 1 over P of yi given theta s, so that's just a draw from our posterior, calculating the likelihood using a draw from the posterior, it's proportional to the ratio of the posterior density for that parameter given the leave one out distribution to the full distribution. Then the importance sampling leave one out predicted distribution, IS Liu, is given by this formula here. We're basically multiplying it by the importance ratios as weights and then dividing it by the sum of those importance ratios to standardize it. And if we evaluate this at our left out observations, it simplifies to this formula here. Next, please. However, the weights are estimated of a long right tail, indicating high or infinite variance. So to reduce the influence of a few very large importance weights, we can smooth them with a generalized Pareto distribution using an empirical Bayes estimate, shown by Vittori et al. So this is called Pareto smooth importance sampling, or PSIS, and it proceeds in 3 steps. First, we fit a generalized Pareto distribution with the upper 20% of importance ratios S separately for each held out observation I. So for each observation, we're fitting a separate Pareto distribution to those high ratios. Then we replace these 20% with the expected values of the order statistics of the fitted distribution for each observation I. And then finally, to guarantee finite variance, we truncate each vector of weights based on the average of the S smoothed weights estimated for that held out observation. Next. And then finally, the resulting weights are combined into the PSIS estimate of the Liu expected log pointwise predictive density given by this formula here. And this proceeds extremely fast compared to doing a full leave one out cross validation. And then finally, we have an added benefit that the estimated shape parameter k hat of the generalized Pareto distribution can be used to assess the reliability of the estimate. The rule of thumb is you get good performance up to k hat equals 0.7, which means it's a finite mean, but an infinite variance. But in the fit values, there will be a finite variance. But if it's larger than this, then Vittori et al. Recommend using k-fold cross validation, maybe like 10 folds, but that's much slower than this process, but you get a more reliable estimate. Next. Now to compare this quickly to information criteria, we can use information criteria to obtain a theoretical estimate of the ELPPD. The idea is we start with the LPPD, which again is an overestimate, and subtract a penalty for the number of parameters being fitted. If we consider the predictive accuracy for a given point estimate theta hat MLE, so fit the parameter fit by maximum likelihood estimation, rather than the posterior distribution, then the AIC gives an estimate of the expected log predictive density. Here. You can see this matches what we have in class, except it's not multiplied by -2. There are problems with the AIC, however. It assumes a linear model, a flat prior, and multivariate Gaussian posterior, and a large n relative to p parameters. And it uses a point estimate rather than the full posterior. So it might it might be overly optimistic again, not incorporate that additional uncertainty. Next, please. So the WAIC is an alternative to the AIC, a widely applicable information criterion. And it's a more fully Bayesian approach. It's computed pointwise. So we take the LPPD hat that we saw on a previous slide and subtract P hat WAIC, where P hat WAIC is the estimated effective number of parameters. So whereas the AIC used the actual number of parameters, this estimates an effective number of parameters using the sample variance across simulated draws from the posterior for each observation. So that's the variance here is computed within a set of draws of the parameter from the posterior. Next, please. And the WAIC estimate of the ELPBD closely approximate that of leave one out, or PSIS LOO, though it may be more biased towards the LPPD. But in examples, they are usually extremely close. Both are computed pointwise, and we can use the central limit theorem to calculate their standard error. We can then use the standard error to compare estimates between candidate models more clearly than AIC or BIC. Whereas with AIC, if we see that two models have very close values, it might be difficult to choose between them. Using WAIC or the LUCV, we know relatively how far apart those values are. Next, please. So now to show an example. So for this, I use the radon data set, which is given in Gelman and Hill. It's on radon levels in houses in the state of Minnesota. 919 observations of 4 variables. The outcome is log radon. So this is the radon measurement from a house. There's log uranium, which is the uranium levels in the county. So that's a variable at the county level. Floor, which is an indicator for it's the basement or the first floor of the house where the measurement was made. And finally, county, which is the county name. It's a factor variable, and there are 85 counties in this data set. We'll use PSIS-LU and WAIC estimates of the ELPD to evaluate pool hierarchical models for these data. And I'm just using 2000 draws from posterior, using the RStan ARM package, which connects a stan as a Hamiltonian Monte Carlo method. Next. So here are the 6 models I fit. Each one has log radon as the outcome, and it controls for floor at the individual level. But the second model in each group also adds a control for the county level log uranium. And then there are 3 sets of models: pooled, where I don't incorporate county; separate, where county is included as a variable, but in just a individual level model, non-hierarchical; and then finally a hierarchical model, where there's a random intercept for county. Next, please. So we can see the estimates of the leave one out predictive density for each of these models. So in the output here, we see the ELPD-LU, which is that estimate that is our sort of target estimate. We can compare between the different models. We want it to be less negative. So we see from the first and second model, it improves. The third model is better than the first, but is worse than the second. The P-LU shows that effective number of parameters estimate. And then the final line here is it does multiply by -2 in case you do want to compare to that sort of historical AIC. Next, please. Then we see these other 3 models. We see that using separate, the separate model that also includes a covariate for the county level uranium measures without grouping those in a hierarchical structure performs very badly. And then we can see the hierarchical models perform quite well. In a bit, I'll compare all of them explicitly. Next. Here is comparing leave one out cross-validation, WAIC, AIC, and true leave one out cross-validation. And we can see that their estimates for the ELPD are almost exactly the same, which is pretty remarkable. But this is generally true for the LU and the WAIC. The AIC here is usually not the same. It usually is somewhat biased, but in a simple model, it actually does give the same answer in this case. And we can compare these explicitly using those standard errors, and this package will rank the answers. So we see the second hierarchical model with the most controls does perform the best, but it's the difference between the 2 models is only slightly bigger than the standard error of that difference. So we can say the models, the second pooled model and the second hierarchical model are actually quite similar in their predicted performance. Next, please. And you see the same comparisons made using WAIC give us basically the same results. The numbers are off only slightly. And that's the end. Thank you.
Thank you, Nathan. So is the conclusion from the analysis that you will go with the pooled second model?
The second hierarchical model performed the best. But the, oh, you mean because the pooled second model and the, I mean, they're almost equivalent.
Right.
Oh, so you were saying that we choose the most parsimonious model with the pooled
That's
second
right.
one? Oh,
Yeah,
yeah, I guess so.
Yeah. Yeah. Thank you. Yeah, this is a very nice introduction. Yeah, very nice presentation. Thank you.
Thank you.
Okay, so let's move on to Greg, right? And so this is from a Bayesian perspective, while the ones, the AIC we talk about in the class is more from a frequentist perspective. And I think the key here, the difference between what you presented and the BIC is that we consider the prediction distribution here, while in BIC, we only consider the posterior. Yeah. All right, so Adam, you're next.
All right, thank you. So I'll be chatting about Bayesian sensitivity analysis for unobserved confounding. So next slide, please. And I'm going to kind of give a high-level introduction into causal inference in observational studies to start. In general, investigators want to be able to talk about quantities, not just associations. And for our purposes, we'll think of this as kind of like treatment effect, right? So causal inference requires analysis of counterfactuals. So we want to ask questions like, would a patient's health have improved if we had given them a certain medicine? And the typical way to kind of investigate this, or maybe the best way, is with randomized experiment. But for various reasons, those are often impossible or unethical or very expensive. And so we're often left just with observational studies. And causal inference from observational studies will always require an unverifiable assumption or set of assumptions to kind of bridge the gap between the observational data and what you would have had in some sort of randomized experiment had you been able to run one. And these assumptions are what allow us to identify counterfactual quantities with observed quantities. And then after doing that, we kind of do our best to, or maybe before rather, we should do our best to make arguments about the plausibility of these assumptions. And one of the tools to do this is sensitivity analysis. So next slide, please. So a little bit more on identification, just because it's important. So there's a lot of different identification strategies that you can use in observational studies, but each of them requires a different set of assumptions that may or may not be plausible depending on the application. But the crucial thing is that these are different from estimation strategies like regression or matching or what have you. Identification uses assumptions to equate counterfactual quantities. So in our case, like a treatment effect with observed quantities that come from the data. So that's really important. Next slide, please. Okay, so we're gonna focus on the identification strategy that I'm sure many of us are aware of, which is no unobserved confounding. And it goes by a series of different names in different literatures. But the main idea is that there are no unobserved variables that create a spurious association between treatment and the outcome. So connecting it to randomized experiments, it's like mini experiments within strata of covariates. And this lets us identify the causal average treatment effect. However, in practice, this is often indefensible in a strict sense. Usually there's something that causes at least a small amount of confounding or bias in our treatment effect estimate. So next slide, please. So to cover a couple quick examples. So unobserved confounding can be related to data limitations. So in this example, we want to know how SSRIs affect risk of suicide, but SSRIs are often taken by people who suffer from depression, and depression itself is a risk factor for suicide. And so if measuring or observing depression rates is difficult, as it sounds like it is from what I've read, we might have this risk of unobserved confounding. So next slide. So unobserved confounding could also be related to hypothetical unobserved variables. So, we all suspect that smoking increases the risk of lung cancer, but there's this hypothesis that people who smoke might have a smoking gene that both causes them to smoke as well as have higher rates of lung cancer. But that's just a hypothetical variable, hasn't been identified, and there's no data on it. But that doesn't mean that there isn't some amount of unobserved confounding when you're, doing an analysis of smoking as it relates to lung cancer. So next slide, please. Thank you. Hence, we do sensitivity analyses to evaluate how the results of a causal inquiry would change as a result of violations of our causal assumptions. So here we're going to focus on violations to the no unobserved confounding assumption. So specifically, we want to know if we allow for the existence of some unobserved confounder, how might the treatment effect that we've estimated change? And that's the little picture that might be useful to have in mind. So Z will be our unobserved confounder. Okay, next slide, please. So in a traditional, quote unquote, sensitivity analysis, we're interested in thinking about the bias due to unobserved confounding. So how the naive treatment effect would differ from the treatment effect that we'd get if we were able to control for the unobserved confounding. And this bias can be expressed in terms of sensitivity parameters. And those are usually, in this case, measures of the association between the confounder and the association between the confounder and treatment and the confounder and outcome. And it's worth noting that this bias expression will need to be derived for different types of models. So whether it's like a logistic regression or like a simple linear model, whatever, like the bias expression will be different. And so that can be an impediment. And then once you have this bias expression, you kind of evaluate over a grid of the possible sensitivity parameters and to see how the treatment effect would change. And then you use, the relevant literature, your expert knowledge, external data, whatever you have to evaluate which values for those sensitivity parameters are actually plausible. And this should sound kind of like a prior over the sensitivity parameters, but in traditional sensitivity analysis, it is not an explicit formal prior that you put over the parameters. And so next slide, please. So here's a quick example. I'm sure this is familiar to many of you. This is omitted variable bias. And so if we're interested in the effect of X on Y from the regression where we also control for Z, but we're only able to run the regression with just X, we can show how the coefficients from those two regressions, the coefficients on X, we can show how those two relate. And it turns out that the bias can be expressed as a function of two parameters, one that relates Y and Z, and one that relates X and Z. So the confounder and the outcome, and the confounder and the treatment. And then you can hypothesize values for those two parameters, in this case, the regression coefficients, to find what your unbiased treatment effect would be. And in that, you use the biased treatment effect, which is that delta X. So that's kind of like the simplest approach to this. Next slide, please. And so while that's, using that would be great, and if more people did sensitivity analysis on their, work, that would be a benefit in general. But McCandless and Gustafson and others also advocate using a Bayesian approach, where you actually put a formal prior over your sensitivity parameters. And this prior, again, should incorporate the relevant literature and expert knowledge, et cetera, to, you have kind of the best prior that you can have for your scenario, or use an uninformative prior. And in this Bayesian version of sensitivity analysis, you don't need a bias expression. Instead, you introduce the sensitivity parameters directly into the model. And kind of the main benefit of this is that it allows for sampling from a posterior that includes uncertainty from both sampling and from the unobserved confounding. which is not the case in kind of the more traditional version. There, you're kind of doing this analysis after your estimation, where you are trying to decide, which values of these sensitivity parameters are plausible. Here, it just is all done, as you find your posterior, or once you find your posterior. Okay, next slide, please. So in this kind of simplest form from this paper from McCandless et al., the general approach is to model the outcome treatment relationship. Then, as I said, incorporate unidentifiable sensitivity parameters into the model, put a prior over all the model parameters, including those sensitivity parameters, and then use Bayes' theorem to find your posterior. And that posterior, again, will affect both the uncertainty from sampling error as well as from unobserved confounding. And in this paper, as well as the others that hopefully we'll have time to get to, the focus is on binary data and logistic regression, and the application for all of these papers actually is looking at beta blockers as a treatment for preventing heart failure. So next slide, please. Okay, so here's the model. And as you can see, both Y and Z. So Y is our outcome, and again, Z is our unobserved confounder. They're both formulated as logits. And you can see the coloring is the same here. So the treatment effect that we're interested in is that beta X. And then the sensitivity parameters that we saw before are in red. So again, one of them governs the outcome confounder relationship, and the other is the treatment outcome, the treatment confounder relationship. But it's worth noting here that we also introduced observed covariates. So that's what our C is here. And so we also need to specify priors over those parameters as well. And we will address difficulties with that in a second, hopefully. So next slide, please. Okay, so these are the priors from this actual application. So you might want different ones in some other setting. But in this case, the authors specify uninformative priors over all the model parameters, but they choose to use uniform priors over the sensitivity parameters, kind of emulate that kind of search over a grid of possible values that you get in a more traditional non-Bayesian sensitivity analysis. And then the authors use these priors and their model to find a posterior for the treatment effect that incorporates both of these sources of uncertainty. And of course, altering the priors, if you have a lot of information on the treatment, if you have a specific confounder in mind and you have a lot of information on how that confounder relates to the treatment, you can have a much more informative prior over that coefficient or whatever other coefficients you might have more information on. That will change the posterior. Next slide, please. Okay, so that kind of simplest version of BSA is great, but there are some difficulties. So if you have a high dimensional set of observed covariates, there's a lot of priors to specify. It's often unreasonable to think that your unobserved confounder and this high dimensional set of covariates, observed covariates, are not related. But you don't know the way in which they're related, so you want to maybe allow for some interaction terms. So anyways, we arrive at the need to specify many priors for many sensitivity parameters. That can be difficult in its own right. But we also might want to borrow some information from the confounding that we see from our observed covariates to learn about the confounding from this unobserved covariate. I'm realizing U here should have been Z. I apologize for that slip in notation. So kind of to solve these problems, you can use hierarchical models to reduce the number of parameters as well as share information across those parameters. So that's kind of like an additional improvement. Next slide, please. And finally, there's kind of another flavor of probabilistic sensitivity analysis. It's not called Bayesian that's out there. And here it's Monte Carlo sensitivity analysis. It doesn't formally use Bayes' theorem. Instead, you sample values directly from the priors, and you use a bias expression again, as in the non-probabilistic approach. And the idea is that you won't learn anything from or about the unobserved confounding from the data. And so you won't actually need to formally use the use Bayes' theorem. And here in this application, this is the expression for bias. They can, they differ based on the application. But what the authors find is that Bayesian sensitivity analysis can actually perform better because there can be certain sets of sensitivity parameters that are not consistent with the data. So BSA usually, or maybe not usually, but can, in some cases at least, outperform MCSA. Okay, next slide. Quick conclusion. So as I just said, BSA can outperform MCSA. Hierarchical BSA is more flexible, and BSA formally integrates the data and the priors to find a posterior that incorporates these two types of uncertainty. So uncertainty from sampling, of course, and also from unobserved confounding. In general, though, just conducting any sensitivity analysis is a really great thing to do, and it improves, moves you towards more credible causal inference. And then references are on the last slide.
Thank you, Adam. I think my only question is regarding how can you say the BSA outperforms MCSA? So the outperformance is defined in what sense?
Yeah, so in the sense that the posterior for the treatment effect is not the same as its prior. And so if I'm being honest, the authors don't go into, this was the paper that I spent the least time on, but the I don't remember the exact mechanism through which some sensitivity parameters are ruled out, but the idea is that there are some sets of sensitivity parameters that are not consistent with the data, and therefore formally integrating the priors and the likelihood will get you a narrower interval estimate than if you just sample directly from the prior. Does that answer the question, or am I missing something?
Yes. So because I feel like the MCSA, based on your description, is very like what people call the approximate Bayesian computation. It's something like
exactly. And I think I'll make sure I explain that more fully in my paper for sure. But I think that high level idea is the reason, and I'm a little unclear on the mechanics. I apologize for that. I should have.
No problem. Yeah, I look forward to your paper. Thank you.
Thanks.
Thank you. Let's move on to our next speaker. So Dongyu, I think we have a skip, right? So we'll move on to Greg and Derek directly. Okay, please go ahead.
Sure. Okay, so our presentation is called Big Questions and Medium Data, the application of multi-level regression and post-stratification in political science, or MRP for short, or as we call it, Mr. P. Next slide, please. So just a roadmap for quickly where we're going to go. So first, I'll talk about the substantive interest, so why we want to use this method. Essentially, we're studying representation, which involves estimating subnational levels of public opinion from national surveys. I'll briefly overview some previous methods for estimating public opinion, and then talk about the method we're going to be overviewing today, multi-level regression and post-stratification. And then Derek will talk a little bit about its current applications. We'll go into some recent advances and augmentations of the model and some recent papers that have been done. Next slide, please. So the major question, one of the major questions in political science is one which is a subject called representation. And so essentially this question is wondering how the behavior of elected officials, so when they vote on bills or when they engage in elite activity, mirrors the public preferences or the preferences of their constituents. So you can imagine if you're a Congress member and you represent a certain district of people in whatever state, the question is whether or not you're voting on things like same-sex marriage or welfare increasing or the LGBT rights, and whether or not those votes are in line with the public opinion of your district. So in order to measure that, one of the difficult things is getting an accurate portrayal of what the public opinion looks like in different elected representative districts. Next slide. So for a long time, it's been tough to sample enough Americans or enough people in the United States to get an accurate representation at lower levels than national. So for instance, our largest survey, or typically would have been our largest survey, only has about 2,000 respondents in it. And so you could think even if the geography was equally distributed throughout the United States, there would only be about 50 people per cell. And it's just not quite enough to provide reliable estimates. Even if it was, since it's not equally distributed, you often have maybe 3 or 4 people in a certain state. And that's just not enough people to produce reliable estimates at the state level. Even today, we have our biggest survey every 2 years has about 60,000 people in it in total. But again, that's a problem when you're trying to look at state legislative samples, like maybe state assembly or state senate, where there are thousands of those. And so you just don't quite get enough people to provide reliable estimates for trying to do disaggregation. So we've tried to come up with alternative ways to get good estimates of those. Next slide, please. So the first method goes back to 1965, I think, when they were still using these huge computers to do it. And so this is a method of estimating state level public opinion from national surveys. So essentially they create a few hundred voter types using demographic and geographic factor variable combinations. So you can consider, they take a bunch of national surveys and they pull them together. They take about 10 years of surveys and they pull them together and they try to find some variables that they can, that are the same across each survey. And they come up with 7 categorical variables, each with different levels. So you can see if you have something like, they will disaggregate you into city type. So you'll have like rural, urban, and other, or by sex or race. Essentially multiply the levels of these and you get each different possible voter type. And so you could imagine like a data matrix where you have 1 row for each voter type, and then 1 column that has the amount of people that exist in each of these voter types, at least from all the polled surveys. And then the other columns, you have essentially YI predictors that are predicting the public opinion in a certain state. So it could be, think of it as a binary predictor or a probability predictor. Next slide. And so essentially you estimate the YI for all those voter type combinations, and then you just weight according to the demographic composition of the state. So this is kind of the earliest method of doing it. It's pretty intuitive and simple. One of the bad things about this, though, is that it seems that 2 states with identical demographic distributions are going to have identical public opinion. And that's a problem. That's a really strong assumption. Some of the later studies that came out on this discovered that actually between state differences, even if they have almost identical demographic distributions, can be as large as the differences between voter types. So that's obviously an assumption we need to move beyond at some point. Another problem is you needed about 10 years of surveys to get enough sample size to do this efficiently. Go to the next slide, please. So the next method, they decided, why don't we make this even more simple, which actually makes a lot of sense, but again, takes a ton of data. So disaggregation kind of became dominant through the 90s and early 2000s, and this is simply calculating the percentage of public support within each state. This is simple and computationally uncostly. Obviously, a drawback is that it requires incredibly large sample sizes. You used to need about 10 to 25 years worth of polls, and this is obviously bad if we're trying to measure something that's unstable. So something like attitude objects. It's really only useful, I think, for partisanship and maybe looking at long-term presidential vote trends and stuff. Another problem is that given the way that we do polling, a lot of polling is clustered, and so they'll draw extra draws from places just for convenience. And so that's going to make it not representative at certain geographic levels. Next one, please. All right, so now we've been using most predominantly, and what there are recent advances on, is a method called multilevel regression and post-stratification. Essentially, this is just another way of estimating state level or effective way to estimate state level or lower public opinion from national surveys. Uses the best features of simulation aggregation. So in the case of estimating public opinion at the state level, national surveys, individual responses are modeled as a function of demographic and geographic predictors, and you partially pool respondents across each state. Here, and unlike the simulation method, the geographic location of the respondents is used to estimate the state level effects. So these effects are modeled using state level predictors like region or geographic level demographics. So regardless of which actual state a respondent lives in, all respondents in the survey are providing information about demographic patterns that are used to help the state's estimates. And then those respondents from a particular state or region are in turn used to provide more information as to how much predictions within that state or region vary from others after controlling for demographics. So it's a multi-level model. You have the individual level covariates and then pooled data. And estimates are post-stratified as a final step and weighted by each state, by the demographic characteristics of each state. Next. So this is just the setup of the model. So it's the prediction of the support. So you can think of it as like probability of support within each cluster level. So you have the individual level covariates, and then you have state, which is modeled. So each of these covariates, like these categorical variables, are drawn from a random sample or from a distribution of 0 between the variants. Next slide, please. So state effects here model as a function of region and then also religion. And then region is also a model effect. Next slide. And then so this yields 470 or 4,704 possible combinations of cell C. So if, for example, one person here could be given all the categories and independent variables: white, male, age 18 to 19, not a high school graduate, and live in Alabama. And each cell is going to have its own prediction, so its own theta C, and then you just weight that by the sample size from each cell. Next slide. So the weakness of this is it's computationally costly. It requires a lot of geographic data and stuff that might not be immediately available. However, the strength of that, it provides highly reliable estimates. So if you're trying to estimate something at a very small level, so state senate or legislative district, you only need about 5,000 N. And it shows that you have to be comparable compared to much larger N. And then 2,500 for congressional district estimate, 1,500 for state level estimate. It yields smaller errors, higher correlations, and lower variance compared to other methods like disaggregation or presidential vote share. It can also help correct for a lot of the clustering problems that could be associated with pulling tons of surveys together. Next slide.
Cool, so I'll take over. One of the earliest examples of using Mr. P was in Lax and Phillips in 2012, which follows their 2009 APSR piece on gay rights and expands this to a bunch of different policy areas. And their major question is, across multiple policy domains, does policy opinion translate into policy action at the state level? And they measure this in two ways. The first is congruence, which is whether or not opinion majorities translate into policy that is complementary toward those opinion majorities. And also responsiveness, which is whether or not greater opinion percentages lead to higher policy likelihood. So in order to do this, you need a state level estimate of policy opinion across all these policy domains. So what they do is they model these 39 different policies using data from 41 national polls from 1999 to 2008, totaling about 80,000 responses. And similar to what Greg mentioned before, they're using a logistic model here with modeled and random effects. And what they need to do is estimate 4,896 possible combinations for theta, and then weight each of those using the 2000 census. And then the religion is a state level indicator because it's not available in individual level surveys usually or in the census. And their finding, which is shown on the right there, is that policy is generally responsive, but not congruent. Typically, policy tends to be congruent only half the time with opinion majority. So on the right side, you see sort of the S curves of the policies. So the rate at which the opinion is translated into actual policy outcomes. The solid curves are relationships that are significant, the dashed curves are not, and then the percentages show the rate of congruence at the state level. Next slide, please. And then the next major advancement here, which was a huge data project, was Tassanovich and Warshaw in 2014, which asked the question of how well do municipal governments represent their local constituents. And here we find a small advancement in the MRP literature, which is using IRT as the outcome variable. So what they do is they model individual conservatism for about 250,000 Americans using IRT, and they model that estimated conservatism using the multi-level model with these effects for race, gender, education, and then a double nested effect for city and for state within that model. And what they find is that in general, municipalities are very responsive to constituent ideology with fairly little influence from institutions. And you can also see here on the chart on the right that you're able to get some within state variation of city level estimates, which is something that you wouldn't be able to do if you were just using traditional survey techniques. Next slide, please. And we're also going to talk about a few advances here. The first is dynamic MRP. While most MRP estimates are sort of static snapshots of opinion, researchers may be interested in how that opinion changes over time. And so typically the estimate of MRP is independent. You estimate MRP independently on these different time separated data. So you run the model multiple times on different time intervals. But Gelman has a working paper in 2018, which proposes MRT, or Mr. T for you 18 fans out there, which takes advantage of partial pooling to estimate time-varying opinion in a single model. So for example, one of the models that they use includes a year smoother, which is a fixed effect for, are using a continuous variable for year and year squared, and then having a bunch of model to random effects within the model, which, next slide, please, is shown to outperform traditional measures of MRP for time. This is the root mean squared error compared to a bunch of state polling with the traditional MRP measures in red. And you can see that there are a lot of models for Mr. T that actually outperform this. Next slide. And then the final thing we'll get to is the advancement from BART. This is proposed by Bisbee in 2019, which is using Bayesian additive regression trees with post-stratification for BART to non-parametrically estimate opinion in subgeographies. And so what this is doing is using a sum of trees model to non-parametrically estimate these state level opinions. And a full discussion of regression trees is beyond the scope of this presentation, but the logic sort of mirrors that of multi-level regression, where the effects are sort of nested within other effects. And so the parameters of the tree model are assigned to X, which is a partition of which is the covariate space with the function G, but given the tree structure T and the vector parameters at the terminal nodes of the trees M. And so the estimation proceeds using Bayesian regularization priors for T, M, and sigma. And the advantages here are that we can get deeper interactions without researcher specification, and it better regularization insulates from a lot of the data sparsity issues that may exist otherwise, which outperforms MRP on mean absolute error and for the interstate correlation that Greg mentioned earlier. Next slide. And so just to wrap up, MRP is a rapidly developing and popular tool for researchers interested in subconstituent opinion estimation without access to massive data. While still sensitive to overfitting concerns, like we mentioned, there are recent advances in regularization techniques that offer researchers much more leverage than before. And additionally, multi-level models are becoming increasingly popular in experimental survey work, such as Jensen et al., which applies multi-level models to conjoint experiments. So it may not be long before we see techniques similar to MRP in the experimental context for generalizability beyond simple treatment effects, defining what the treatment effects look like at these different subconstituencies. And that is it. Thank you so much.
Thank you very much. This is a very comprehensive introduction. So I just have one question. So regarding the use of MRP, so it's a very, I would say, high level question. Did you want to use the model fitting to help you stratify your data? So in other words, you don't want to stick with the original stratification you can define based on the predictors, the categorical predictors, but you want to combine some of the predictor levels based on the model fitting. Is that a general idea?
Yeah, so the general, yeah, I think that makes sense. I mean, the general idea here is that we want to borrow power from a lot of these other combinations of the variables. So I think
does it mean that you will fit the model, the two different models for twice? So one using the original predictors, the second based on the stratification you define?
Based off of the stratification. I'm not sure I'm following exactly what.
Yeah, I guess my question is regarding the general idea of MRP. So by the name, you want to do stratification, but I couldn't see from the presentation how you did the stratification exactly.
So the stratification comes after running the multi-level model. Then it's just essentially weighting to the composition of each state. Once you estimated the probably or the support, the YI for each cell or each state and voter type or whatever, then you just match those to the demographic composition of each state using just the general weighting scheme. That right there. Yeah. Yeah.
So the model gets fit. So you have all these different combinations, and then the model gets fit, and so you know what the actual distribution of, or what the margin of these
Oh yeah,
combinations are making cells.
I could have made that more clear. Yeah, so you essentially take like census data or ACS data, and then so you know the exact proportion of each voter type that exists in a certain state or district, and then so you weight your findings or your results and your for each voter type or theta C to the demographic composition of each state.
Right, so I can understand this specific scenario, but just in general, when you apply the MRP, you need to first know which predictor you care about. Like here is the state. You have to do that, right? So it's not just like you can do it without any prior knowledge.
Yeah, I think that matters, and that's going to determine which of the regional variables and how you're going to develop their effects. So say you wanted to do district level, right? Then yeah, then you're gonna have to fit a different model that includes information on each district, as well as each state and each region, whatever. Yeah, so you do have to know that beforehand, and that'll influence your model.
Right, and so as Derek talked about the BART in the later part, so that becomes like not a probabilistic modeling approach, but just a classification or regression tree approach. So over there, when you use this approach, you still have that multi-level structure, but you are no longer doing multi-level regression or multi-level the model-based regression, I would say. So here, if you do this approach, you will still use the MRP at the end by giving the weights to different cells, or here it becomes different nodes in the tree.
Yeah, exactly. Yeah, so the post-stratification process is still the same. This is just the estimation of theta.
Okay, thank you. All right, let's move on to our next presentation.
Yeah, so
so Dongyuan, I think, so are we going to have a recording now?
Yes,
or?
yeah.
Probably I think we will defer all the recording to the end, because I think it doesn't matter whether we do it first or later. So you don't have to switch the screen. Let's continue with the slides.
Sure, yeah. Then we will have Lifeng and Kangcheng for the presentation.
Okay.
Hi, I'm Lifeng, and my teammate is Kangcheng, and our presentation today is on the computational techniques for linear mixed models. And next, please. So first, I will introduce a little bit about the basics of linear mixed models. So as we all know that the linear mixed model is an extension of simple linear models, and it is a method that allows both fixed and random effects for analyzing data that are not independent, that are non-independent, or multi-level, hierarchical, or longitudinal, and or correlated. So here is like a general form of this model. It's a y equals to x times beta plus z times u plus epsilon. So here we suppose that u is subject to a normal distribution with zero mean and covariance sigma square u times identity matrix. And the epsilon is subject to a normal distribution with zero mean and epsilon e square identity. So in this model, we have our outcome variable in this dimension n times 1, and our matrix of x is our matrix of p predictor variables, and is in dimension n times p. So beta is our fixed effects coefficients that we want to estimate. Is in p times 1, and z is the design matrix for r random effects and n groups. So here u is the random effect coefficient parameter, and is in nr times 1 dimensions, and epsilon is our random error, is uppercase n times 1. So our goal for this linear mixed models is to try to estimate the parameters, and all the parameters here is sigma u square, sigma e square, and beta. So we want to first estimate sigma u square and sigma e square, and for beta, we want to have a hypothesis test to see whether it's there or not. Next, please. So here's a standard procedure for us to do this. Firstly, we can define K, the Z times Z transpose as K, and a ratio, a variance ratio as sigma E squared divided by sigma U squared, so that we can write our log likelihood like this. It's pretty straightforward. It's a log likelihood of normal PDF with the mean X beta, and the variance is sigma U squared times K plus sigma E squared times identity. So we can expand this PDF and do some manipulations of this this term, so that we get to the final representation using K plus delta I and sigma U squared. So that by MLE, we can estimate our we can get our estimations of beta and the sigma U squared. First, we set a partial derivative with respect to beta, so that we get beta hat equals to this kind of weighted linear square estimates, which I guess is familiar to everyone here. And next, we can set the partial derivative with respect to sigma U squared to 0, so that we can get the sigma U squared hat as a result of this. And also, they plugged in the beta hat into this term and into this representation here. After we have calculated the MLE estimates of beta and sigma U squared, we have translated, we have written our log likelihood in terms of only one dimension parameter delta. That we have our proxy likelihood of LP delta. As long as, because we only have one dimension parameter of the delta here, we can use a very simple optimization method, say Brand's method, which is a hybrid routing finding algorithm. So this algorithm has a reliability of like bisection, but it can be as quick as some of the less reliable methods. So now the only remaining bottlenecks of this calculation procedure is trying to evaluate the likelihood with respect to different delta values. Next, please. So Kangcheng will, yeah.
Okay, so before we talk about some techniques for like overcoming this evaluating the likelihood of computational burden, I want to first talk about some applications that. So linear mixed model is widely used in statistical genetics, especially in genome-wide association study, where the goal is to associate the genetic factor with some disease risk, where the genetic factor will be an n by p matrix, where the number of individuals is n and number of variable would be p, and the linear mixed model approach would be formulate as a linear mixed model, so that here the fixed effects would be covariates such as age, sex, or environmental factors, and for each SNP we would extract that column as the GJ, and also as a part of the fixed design. And for the rest of the SNP, we would formulate that as the rest of the genotype as the random effects. And our goal would be testing a null hypothesis where the quantity would be whether alpha j is 0 or not. And we would need to estimate the sigma u squared and sigma e squared and test the alpha j, whether that equals to 0 for each SNP. So you can see that would be huge computational burden, where the p would be at the magnitude of like 500,000. And in the figure, we show a like example Manhattan plot for genome-wide association study. So on the x-axis would be each SNP, and which is each variable, or you can think of that as each gene. And on the y-axis would be the log 10 p-value, which would be the association strands between each SNP and the disease, for example. Next slide, please.
Okay, so when we apply these linear mixed models into real life problems, there are some difficulties in calculation, so that we have there are some optimization computation methods in different studies. And here we introduce one is called spectral decomposition, which can be used to speed up the iterations in the calculation. So that we have P defined as D times D transpose. So it's a real symmetric matrix, which can be sure to diagonalize. So we can write it as the U times S times U transpose. Here, U is eigenvector, is a matrix of eigenvectors, and this U are orthogonal, so that U transpose is just identity matrix, and S is the diagonal matrix with is the diagonal elements are the eigenvalues, so that we can like plug this into our log likelihood to do some like manipulations of the terms. We can get into the format like this. So we can finally the U transpose will be applied to the Y and X beta, so that it's projected into another dimension space. And what is left here in the variance is S plus delta I, the inverse of S plus delta I. And as you can see that S plus delta I is just a diagonal matrix, which is a pretty amazing, a pretty good result that it is very convenient to calculate its inverse now. And the complexity now is just linear in N for each iteration. And we only need to perform one spectral decomposition. So I think this is typo here. It's not SVD. It's a spectral decomposition at first and reuse it later in every iteration. And these techniques are used in like studies like this in these two reference papers, Fast LMM and JAMA, and which we can use this trick to get exact results. Next, please.
Okay, so we could also have some approximation method. So if we denote the hand matrix and the projection matrix from the linear mixed model as H and P, we could we differentiate the log likelihood with regard to the variance component estimator and set them to 0. We could see the first order conditions will satisfy the following equation. This is straightforward, and consequently, we would arrive at the equation from the last two lines, and these are still standard results. Next slide, please. And given some sigma u square and sigma e square, we could actually calculate the blob estimator estimation of the random effects and error terms. And for example, of some observed data, which is the data set we are given, we could given some sigma u square and sigma e square, these are standard results for u hat and e hat for this observed data set. And here we have some nice trick that we could also do the same for some imaginary sampling data. So still we are using the same Z in the data set, and we could sample from imaginary data with Y random. We could sample the U random from the corresponding distribution, and also the E random from the corresponding distribution, and we could make up some data and also apply the blob estimation formula to those random data. And we could verify the following equivalence to the first order equation for a linear mixed model. That we could write the original first order equation as the expectation of the covariance of the U random, U hat random, equal to the U hat for the observed data, and same applies to the random error vector. And so we translate our problem into into another equation, and you can see that annotated by the red font, there's still some form of matrix inverse and matrix inverse and the vector dot product. And in fact, we could use conjugate gradient to calculate these values. So in reality, we could sample, let's say, 10 random data sets and solve this equation to get the estimate of the U estimated sigma U squared and sigma E squared. Next slide, please. And finally, we show another approach that formulates the problem as the method of moments. Recall that the variance of Y is equal to the sigma U squared K plus sigma E squared I. And we would estimate the using moment matching. And solving this would equivalent to solve the following two-dimensional problem. And we could show that the real computational bottleneck would be the trace of the K squared. And this approach using the following theorem that given any n by n matrix A and a random vector epsilon with mean zero and covariance identity, we could show that the expectation of the quadratic form would equal to the trace of the A. And by using this theorem, we could formulate the calculation of the trace of the K square as the expectation. So we could use Monte Carlo sampling to calculate this value. Right now, we only have matrix vector multiplication right now. So the computational complexity is greatly reduced. Next slide, please. So that's all the reference, and we want to thank, there's a nice video from Professor Noah Zaylan also from UCLA that also have a nice introduction for this method. Thank you.
Very much. So yeah, this is a very nice introduction. I just have one quick question. So regarding the slide where you generate new data from the model, so where you have the new random effects. So what's the purpose of that? So how would it benefit your parameter estimation?
So it's kind of the same idea that if you, let me see if I can. So it will be here that, so we could show that the expectation of the U hat random and U hat would be equivalent to this here. So we could just sample, not evaluating this term, to have some like Monte Carlo sampling approach.
Got it. Yeah, just to save, I see. Okay, got it. Thank you.
Okay, thank you very much.
Thank you. Yeah, very nice summary. So let's move on to our next slide presentation, Ian and Ashley.
Hi, I'm Ian.
Hi, Ashley.
So we'll be talking about subsampling and subdata selection models for regression. Next slide, please. So here's just a quick overview of what we're going over. Next slide. And so here's our introduction. So a very common problem that we typically have in regression is when P is much larger than N. So this is a classic example, and we do things like lasso when that's the case, because as you know, it's impossible to solve that. However, as we get in more big data, there's also the case where N is much larger than P. And while this is technically solvable, you often have computational limitations. So sometimes it's just computationally infeasible to do this. And you also can lead to overfitting. So in the context of regression analysis, when you have this problem, we do something called subsampling methods or subdata selection algorithms. Next slide, please. So the general idea of this is that we attempt to reduce the sample size N, so the parameter estimates are still unbiased. So early on, we'll be talking about methods of data transformation, and then newer strategies also incorporate elements from optimal design theory, like optimal experimental design to achieve what we want to do. So a large part of this is computational intensity, but we want to focus really on introducing sort of a lot of these different methods sort of the intuition behind them, and then just a commentary on like why they're good and why they're bad. Next slide, please. So we're going over 3 types of subsampling methods. So I'll be talking about random sampling on transform data, and then Ashley will be going over methods about D optimality and A optimality. Slide, please. So just briefly notation, N is the number of observations, P is the number of covariates, which is going to be the dimension of the beta vector, and then X, Y, beta are defined regularly. K is the number of observations in the subsample, and pi I will be the subsampling probability for the ith observation. Next slide, please. So for random sampling on transform data, so this is a pretty basic idea. The basic idea is we have some M, some matrix M that's constructed in a certain way. We multiply it to both X and Y, and this acts as both a sampling and a transformation matrix. And then standard linear regression is then applied to the transformed vectors and matrix MX and MY. And the kind of idea is to make it so the leverage is more uniform, so we get good estimates. So we're not just selecting certain values, we're also scaling them. Next slide, please. So there's going to be about 3 papers I'll be talking about. So the first one from Drinius, I believe it's pronounced, 2006. So this is sort of one of the early papers. This is a lot of times mentioned in a lot of papers as one of the earlier ones to do this. To get the intuition behind it, the selection of M actually is depending upon the Euclidean norms of the left singular vectors of X. So we're incorporating that information that way, as well as how Y lies in the complement of the column space of X. So again, that talks about the information about that X is sort of delivering. And I don't want to get too into the technical details, but all these papers will be talking about the L2 norm in general. And in this way, with this paper, we can specify an epsilon and then any epsilon, and then get it so that the L2 norm of the error with our transformed vectors will be less than 1 plus epsilon of our L2 norm of our error for our non-transformed vectors. Next slide, please. So to describe the algorithm in this paper, the inputs are our data matrix and then our selection probabilities. Now, it's important to note that these selection probabilities have to be inputted before, and I'll get into a little about how they're selected. And then we have some value K, which is going to be our like subsample size, okay? And then S and D are created. Notice that they have N by K and then K by K. And then for each element, for each T and 1 to K, we basically pick an element from our X matrix depending on the subsampling probabilities. D then is a vector, is then on the diagonal has a scaling thing that is corresponding to K and then also selection probability. And then S acts as like our selection matrix, basically. Then our M ends up being DS transpose, and that's applied to both X and Y, which I call X reduced and Y reduced. And then we proceed to standard linear regression on X reduced and Y reduced to calculate beta reduced. Next slide, please. Okay, so some discussion. So I left out some of the results, but essentially what ends up happening is we are able to bound, as I described before, Y minus X beta, and then the reduced versions of that. And also we're able to bound the difference between beta from our full vector, the L2 norm of beta minus beta reduced, okay? Now, what's the problem with this? It's actually not computationally better. So to do it, there's a typo there. That bold line should be O NP squared. So standard linear regression is done in O NP squared time, and while our reduced linear regression is done in O RP squared time, selecting the probabilities in the way that's described in this paper also takes O NP squared time. So we're really not helping at all. So next slide. To improve, in 2010, the same author wrote a paper that attempts to fix this computational issue. So the result of this ends up with an algorithm that can be done in the order of ND ln of D time, which is obviously faster. Next slide. So just briefly, we use something called a Hadamard transform matrix, and this is a recursive matrix built in this way. So H0 is just 1, and then for each M greater than 0, HM is defined recursively in that way. And that creates basically a certain matrix that we then utilize. Next slide, please. So the algorithm here, you input both X and Y, which are the same as before, and then some error value, epsilon. So just as before, we can select epsilon. And you'll note that we don't have any selection probabilities anymore, okay? So if K is chosen a certain way, depending on epsilon, as you can see, then we can perform a very similar algorithm where S is, actually, I believe in this case, yeah, S is a scaling matrix and a selection matrix at the same time. H is the Hadamard transform matrix, and then D becomes a diagonal matrix with either 1 or -1, depending with a probability of 1/2 for each. And then our reduced matrices are now S transpose HDX and S transpose HDY. And then we can proceed with standard linear regression. And using this sort of framework makes it so we do not have to pick the selection probabilities, and that we also can have good estimators, basically, as I defined previously. Next slide, please. So then just very briefly, this last paper in 2013 by Deqian, what this does is basically do a 2-stage estimator. So we do what we just did before, and then we add on just a little extra step. Next slide, please. So yeah, just briefly, essentially Y rem and X rem are the remaining values that we did not select in the previous algorithm. Then we use them again, sort of, to create a new beta hat of incorporating information from the remaining values. But notice that we do not have to calculate X remainder transpose X remainder. Instead, we just use the previous X matrices from the selected values previously. And then we just use a weighted estimate to calculate a new estimate. And this has better properties as well.
Okay, so I'm going to move on to the next section. So as you saw in the last two methods that Ian explained, we're kind of relying a little bit on random or uniform subsampling, which, as we know, may not be the best way to actually sample the observations from the full data set. So what the more recent methods that have kind of started to be developed around 2018, they tried to use characteristics from optimal design theory. So a little bit of background on optimal design theory is that we're essentially just trying to optimize our experiments and the way that we collect the data to make sure that we can collect as much information as possible with limited resources or a fixed budget. So there are several different statistical criterion that you can use to, design your experiment in an optimal way. Two of the ones that are used in the context of subsampling and subdata selection are D optimality and A optimality. So as you can see on the slide, D optimality, the D basically just stands for determinant. So what we're trying to do is minimize the determinant of the variance covariance matrix of our estimates. And that's basically the same as maximizing the Fisher information matrix in the context of linear regression. And then for A optimality, the A stands for average. So we're trying to minimize, again, the trace of the variance covariance matrix, but now we're using the trace instead of the determinant. And this has the effect of minimizing the average variance of the parameter estimates. So what we're trying to get at from using optimal design theory is that uniform subsampling probabilities may not be optimal. So there are probably better ways that we can select based on these two different criterions. So next slide, please. Next slide. So the first one I'm going to be talking about is subsampling under D optimality. And there are two different papers that cover this in our overall survey paper. So we have the setting for linear regression and logistic regression. Both of the algorithms there are, more or less the same. There's the same general idea of us trying to maximize this information matrix. The algorithms differ slightly just because of the need for optimization methods and IRLS in logistic regression, but the overall goal, again, is to maximize the information retained in the subdata. Next slide, please. So to accomplish the goal for linear regression, we can recall that the variance covariance matrix of the estimators is also the inverse of the Fisher information matrix, and it's defined there. We've seen this in class several times. So consequently, if we create a subdata, like subselect from that and create a piece of subdata, we can call that X star, and that would be of size K instead of N. So we can reformulate the information matrix then to X star transpose X star, and then of course you have the 1 over sigma squared in front. So we can rewrite that now in terms of the actual full data matrix by using this vector for delta, which is an indicator variable that indicates whether or not the ith observation should be included in the subdata. And then obviously the sum of delta I would be equal to our subset or subdata size. Next slide, please. So under D optimality, we can basically then define an optimal delta that would give us the maximum of the Fisher information matrix. So I'm skipping over some of the mathematics, but basically what the authors do is that they try to estimate an upper bound for that determinant quantity. And what that asymptotic upper bound shows us is that we should be collecting subdata with the extreme covariate values. So both extremely small and extremely large. And the intuition behind this is, very similar to what we saw in class, where extreme data values at the ends of the distribution will be more informative for your parameter estimation than the cloud in the middle. And so I'm going to go through the algorithm in the next slide, but again, this is a deterministic algorithm, and it actually preserves most of the information contained in the full data, which is a very interesting property. Next slide, please. So this is just the general algorithm, and I'll go through it a little bit quickly, but in the first step, you're essentially cycling through all the observations 1 through n, and you're trying to get a group of the most extreme large values and the most extreme small values, and then you repeat that process for all the covariants. And then you compute your estimates in your variance covariance matrix based on that subdata. Next slide, please. So as you can see, this is kind of a picture of what the actual original data looked like, which are the small kind of gray dots. And then if you look at the larger circles, those are actually the data points that were selected by this algorithm called IBOS, which is information-based optimal subsampling. So as you can see, again, that just basically reiterates the same idea where you're selecting the most extreme values. Next slide, please. So again, this is suitable for parallel computing because of the way that we cycle through the covariates. It's deterministic and the overall complexity is improved. It will retain the most extreme values from the data set, which might include outliers, but you can do, you can actually test for the outliers again in the subdata. This outperforms other subsampling methods like the ones that Ian mentioned in terms of MSE by about 20%. And then the interesting key property here that I mentioned before is that the variance of the slope parameter estimators converges to 0 as the full data set goes to infinity. So even if the subdata size K is fixed, so that's a super interesting property because it basically says that our subdata, the information contained in our subdata is only limited by the full information in the full data set, not by our actual subdata size. Next slide, please. I'm going to have to go through this a little bit quickly, but I did want to mention that for this IBOS method, it was extrapolated to logistic regression, but it's a little bit more challenging just because the information matrix is more complicated. And then again, you have to use IRLS to compute the estimates. But the basic idea is the same, is that you want to just maximize the information matrix. But because the asymptotic upper bound in this case actually depends on beta itself, we have to adapt the algorithm to be two-stage, where the first stage is computing a pilot estimate for beta, and then you use the same IBOS algorithm to select the extreme covariate values in the second stage. So the key asymptotic property is actually believed to be retained based on the empirical results, but the authors weren't able to prove it through the complexity that shows for the asymptotic upper bound. Next slide, please. Next slide. Okay, so I'm just going to go through this really quickly, but in addition to D optimality, we can go through an algorithm for A optimality, which again minimizes the trace of the information matrix. So what this focuses on, instead of using a deterministic method, is to actually amend the pi I values, so the subsampling probabilities. And we can do that again by minimizing the asymptotic variance covariance matrix of the subdata estimates minus the MLE estimates from the full data. Next slide, please. So if you look at this formula here, which is the now optimal pi I, you can see that it's a function of the response y and the covariate x. And if you kind of think about that intuitively, the values that you'll get then will actually give more preference to points that are more likely to be misclassified. And the computational complexity of this, as you can see in the slide, is actually, it's pretty computationally expensive. But if you looked at the formula for V itself, you can see that the only portion of V that depends on pi I is actually the subcomponent of VC. So you can actually regenerate pi I to just be dependent on that, and that is going to give you pi MVC. So then you would use those subsampling probabilities to generate your X star subdata matrix in a two-stage algorithm. Next slide, please. So the two-stage algorithm, I won't go into the detail, but it's similar to that for IBOS, where you have to use a pilot estimate in the first stage. And unlike IBOS, which is under D optimality, but similar to the methods that Ian presented, this method uses both the covariates and the response variable to produce the best subset. And in the results, what's interesting is that obviously because the pi that's under MSE is optimized for the mean squared error. So in all the empirical results, it shows the lowest MSE compared to other subsampling methods, but the VC method actually performs the best in classification. Next slide, please. Next slide. So just to conclude our presentation, as we showed earlier, the first few papers that Ian talked about were mainly focused on computational complexity, and then the latter methods are a little bit more about the asymptotic properties and then the implications for statistical inference. Not surprisingly, logistic regression is more complicated. And then the third bullet point is just to say that, there's a lot of other research being done on extending this to more complicated forms of regression, like we saw in the last presentation, where they were using it for mixture models. And so there's a lot of interesting research being done on trying to speed up the complexity while retaining these interesting properties.
Thank you. Thank you.
Sorry, we went a little bit over.
Yeah, I just have one quick question. So regarding the difference or the advantage of the last one, the OS-MAC compared to the IBOS, can you elaborate on that? What's the advantage of using the A optimality instead of a D optimality in terms of statistical difference?
Yeah, it's different because it kind of depends on like what criterion you're trying to satisfy, right? Because for the D optimality, it's just a different way of defining what is optimal. So if you're interested in making sure that the average of the estimates is as low as possible, or the average variance of the estimates is as low as possible, then you would probably want to use the OSMAC instead of IBOS. But in general, if you're looking at something like MSE, or you're looking at, basically if you're just looking at something like MSE, the IBOS method actually performs better than OSMAC. So if you're interested in like the prediction, you might want to use IBOS instead of, which is under D optimality, instead of using the OSMAC, which is under A optimality.
Okay. And related to the previous work, like the 2010, 2013 work, so does the IBOS have computational advantage over those? Because those methods were specific trying to optimize the computational complexity, as you said, like the 2013.
Yeah, so we kind of skipped over the complexity components just because they're all pretty fast. But the paper does show that they are faster than the original methods, because this was developed after those original data transformation methods.
Okay, very interesting. Thank you. All right, so let's move on to our last two presentations, which are video recordings. So Dongyan, you can play them sequentially. So because I think two of the presenters for the second last presentation, Evan and Nada, they are here. So we could still ask questions, but for the last presenter, I think he's not here. So we'll just watch the video.
Okay, sure, yeah. Check. Can you see the screen right now?
Yes. But we cannot hear any sound.
Oh, you cannot hear any sound?
Yeah, I think you need to reshare your screen with the computer sound. Or Dongyan, you need to, so if you cannot share the sound from the app, you need to play the sound out and just let so you cannot wear your earphone. So
okay,
otherwise,
I see, yeah.
Yeah.
Yeah, maybe let me try this.
You can try either way. You can try the share screen with, and you need to check the computer sound at the lower left corner.
Hello, everyone.
Okay.
I'm Dan. I'm a computer science PhD student.
And I am Evan Becker, also a computer science PhD student.
And we'll be talking about empirical Bayesian approaches for multi-level models. So first of all, some motivation. First, why multi-level models? So many domains, biological, social, physical, naturally impose hierarchical structures. And those hierarchical models can be incorporated very intuitively within a Bayesian framework where all of the priors are specified and the model is completely exposed. Now, an empirical base takes advantage of this framework while overcoming some of the drawbacks of fully Bayesian approaches, which I'll talk about in the next slide. So what is the fully Bayesian approach? In the fully Bayesian approach, every parameter comes from a distribution, and every parameter has some prior. And those priors are used to incorporate prior knowledge. Now, this knowledge can be either from an expert, such as a doctor or clinician that incorporate the knowledge he gained throughout the years, or empirical knowledge, such as data from previous experiments. And that knowledge can also be in the form of structure, such as in multi-level hierarchical models. Now, the main interest in Bayesian approaches is to find the fully joined posterior distribution. And the advantages of fully Bayesian networks are Bayesian frameworks are that when you estimate that posterior, you get uncertainties for your prediction automatically. All the assumptions you make are explicit and are shown via the prior and the structure. And multi-level models can be very easily incorporated in that framework. And you can't talk about the Bayesian approach without at least mentioning the posterior distribution, as we can see it here in these two equations, where mostly the focus is on the numerator, as seen in this equation. Now, multi-level models can be shown very easily in a Bayesian framework by using generative models, where the data, y here, is basically generated from some distribution, of y given data, the parameters. And what makes this a multi-level model is that even the parameter data are generated from some distribution of p of theta given theta, which are the hyperparameters. And this can go on and so forth as much as the model or the problem requires. And now, how do we estimate those parameters? So there's several approaches. One is analytical, using something called the conjugate priors. And it works in some cases, but is very restrictive in general, because those conjugate priors, you have to match a specific prior for a specific likelihood, and that's kind of restrictive from incorporating the knowledge in the form that you want. So the other way, which is more popular, is by using sampling in something called a Markov chain Monte Carlo, also known as MCMC. Now, MCMC has its own problems, and those problems come especially in multi-level models. MCMC suffers sometimes from something called divergencies, which is a problem with the optimization, or funnel degeneracy, which produce biased results, and is very common in multi-level models. And also bad mixture, which is the case where the MCMC just doesn't converge into the posterior that we're looking for. And to solve those problems and to produce a solution comes empirical base, in which we basically use data to estimate the prior distribution and acquire point estimates instead of the full posterior distribution. Empirical base is also sometimes known as the maximum marginal likelihood.
So now just talking a little bit more into types of empirical Bayes. Over the years, there's been both parametric and non-parametric methods. Today, we'll cover mostly parametric, but for the sake of completeness, we just wanted to mention both. Parametric, the main thing is you're assuming kind of a tractable prior distribution, for example, normal, which would be parameterized with something like a mu and a sigma. Whereas non-parametric, we just don't know the form of the prior distribution at all. For parametric, we can use a variety of methods to get a point estimate. We could calculate, as Nadav said, the maximum likelihood estimate of a marginal likelihood. We could do something like a map estimate, mode of the posterior. And for parametric, these point estimates are very good when our posterior is very sharply peaked, because then you'll see that the integration that we mentioned in the previous slide comes out to be approximately the same. For parametric, there are also a couple different methods. You can calculate kind of this conditional mean, And there have also been maximum likelihood estimates for non-parametric forms of the prior. So moving on to our outline of covering some of these applications of empirical Bayes. We'll first start with a paper by our very own Dav. It's an epidemiological model of COVID-19, so it's very relevant to today's world. We'll also cover an ecological growth model and a genetic model, which we thought was a good cross-section of real-world applications that demonstrate really the need for hierarchical linear models and nonlinear models, and the advantages that empirical Bayes specifically has over fully Bayesian methods. Namely, they are fast, they're scalable, and they provide a very good compromise between kind of the two major schools of thought in statistics, between frequentist and Bayesian thinking.
Yes, so I'll introduce the first application. And first I'll talk a little bit about what the problem is in our paper called Quantifying the Negative Duration of Social Distancing for the COVID-19 pandemic. So what we try to do here is we try to estimate when are social distancing going to end. And to do that, we use a model from epidemiologic. It's called an SIR model. And basically what we had here is we had to fit a model that had parameters R0 and tau. And with those, we can produce a simulation of when social distancing is going to end, as seen on the figure on the left. And different parameters would provide a different end for social distancing. Now, one of our major challenges was that there was not a large amount of data. And therefore, we had a lot of different parameters that were able to get very good fits on the data and historical data, yet produce very, very different results for our goal of when social distancing is going to end. So one way to address this problem is having small sample size from very different groups was to use hierarchical models, where we basically fitted all these parameters together using a multi-level model. So here's a figure that shows the multi-level model that we use. So for each different region, we had these two parameters, R0 and tau. And then we assume that all the different parameters from the different regions, each of them comes from some shared distribution. In this case, it is normal, with some global parameter, global R0 and global tau. And then we assume that our data comes from a normal distribution with a mean that comes from this function of these parameters in some different. And now we don't disturb, these are the likelihood functions. And then we decided to go with the empirical Bayes to estimate those parameters. And the reason we chose empirical Bayes, the first reason is that it reduced the number of parameters. So instead of estimating the parameters for all the different locations, we just estimated the global one. We integrated over the local one and just estimate 2 parameters, 4 parameters, the global one. And the second reason is that at that time, I didn't know how to implement a fully Bayesian approach. And I think that in general, a lot of the times the applied researchers also don't have the repertoire of the Bayesian programming and probabilistic programming. So empirical Bayes is good because it's simple and it's very easy to implement. And once we estimated our parameters using empirical Bayes, as we can see in the next slide, we're able to sample and get a distribution on when does the social distancing going to end, and also get a general good fit on all the different regions.
Awesome. Now for our next application, we went in a slightly different direction. We chose the growth rate model of marble trout. This paper was interesting because it's a very good example of a typical ecological model where you have lots of structure. There's populations of fish, there's specific cohorts, which is basically the year that they were born, as well as individual level effects. And also this is a nonlinear problem. So this paper specifically used the generalized linear mix effect model, which we thought was interesting because it combines both generalized linear models and mixed effects models, which we've done in this class. Why specifically did they choose empirical Bayes? They chose it because it was fast, generalizable, and really the main takeaway that we got from this paper was that they had no convergence issues compared to fully Bayesian, which they actually were not even able to get to converge to their parameter estimates. And they were able to do this using widely available software packages. Specifically, they use something called ADMB, which is publicly available. On the right, you'll see the general model. What's different from what we've seen usually in class is that this response variable G is actually a parameter used for a dynamic simulation. So this is a growth parameter. For fish I and cohort J, they kept the group effects fixed just for the sake of computational efficiency. But you can see all the way on the right, this variable U is kind of our random individual intercept. So just briefly, here is the specific growth model. This function is kind of like an asymptotic thing where you have three main parameters, this length, asymptotic length, this growth rate K, and T0, which you can kind of think as an intercept for the initial starting length. You'll see here they use a log-link function, which makes sense because, you know, similar to a count variable, you're not going to have lengths be a negative variable. So again, this is an example of using prior information about the problem to assist. For parameter estimation, they used a marginal likelihood, so not a profile likelihood, to find the parameters theta, which you can see in the top right. And then what they did is they just plugged these estimates back into the posterior distribution and found the mode as the estimate for this random effect. So what did they find? So they found that, importantly, using these random individual effects made the model more accurate in terms of AIC than predictions just based on groupings alone. So this you know, reinforces why these hierarchical models are needed. And here's a quote from the paper. When they're dealing with these large number of random effects and missing data, really noisy biological data, the methods, the full Bayesian methods, took a very long time to converge or fail to converge. And so here you can see, interestingly, some of these random effects are correlated. You see the asymptotic length on the x-axis and the growth rate on the y-axis here. Now moving on to our last model, very quickly, we're estimating basically the phenotype response from a couple different genotypes. And actually it's more than a couple, there's a lot. And they really want to see which ones are having the most effect, where most of these genes are actually not having effect. So it's a very sparse model. They use empirical Bayes mostly because it's fast and robust, similar to the last paper. What's interesting is that they include analysis on the specific times as well. So just a brief overview of the model. You have the measured phenotype Y. They have some predictors that are not of interest, X, but are needed to help fit the model, such as environmental effects. And you have a genetic marker of interest, Z. And this, the effect gamma of each of these genetic markers are actually distributed normally, but the variance itself has an inverse chi-square distribution, which the author interestingly uses kind of as a regularizer because the data is so sparse. So parameter estimation at a high level, this is very similar to actually what we've done in class. They find the maximum likelihood estimates, again, over a marginal distribution for beta, sigma squared, and D, which is just kind of the diagonal matrix of the gamma's variances. And then they use an empirical Bayes method for estimating our genetic effect. Gamma, they actually use the biased linear, or the best linear unbiased predictor, which is what we've seen in class before. So importantly, this is what they found. They found that empirical Bayes and SVS, which is their fully Bayesian approach, both did pretty well when estimating the effects of the simulated gene data, right? All the effects are matched pretty closely, as you can see in these graphs. But most importantly, empirical Bayes was almost 20 times faster. You can see SSVS took 500 approximately minutes, while empirical Bayes took about 30.
So to conclude, we saw that the advantages of empirical Bayes is that it's easy to implement, it's fast, and you're still able to use the Bayesian properties such as incorporating expert knowledge and desired structure.
Moreover, there's no convergence issues like some of the fully Bayesian methods, as we saw with our trough growth model. And yeah, it still gives the interesting Bayesian properties that are needed in these biological implementations.
And at this point, we'd like to thank our audience and professor and class. These are the references we use. Thank you all for listening. Good luck.
Thank you for this presentation. I think the speakers are here. I just have one quick comment to say before we move on to our next presentation. I feel like the empirical base, to me, is still under the frequentist framework. So it's more like a hierarchical model, which you fit in a frequentist way. But it has some resemblance to a Bayesian model because you have that prior as your upper layer in the hierarchical model. But ultimately, all the information are from the data. So that's why, to me, it's still quite like a frequentist approach. So therefore, I wouldn't really compare it with the full Bayesian approach because just to me, they are having different perspectives. But it's nice that you give those 3 examples to show, yeah, it's very widely used in applications. So I really appreciate that.
Thank you.
Thank you. Okay, so Dongyan, let's move on to our last presentation.
Yes.
And I think I'm very interested in reading that paper, the empirical base past, present, and future. I think I'll read that one. Yeah, it seems to be a very interesting paper.
Hi, my name is Guan'ao Yan, and my presentation is about the test of zero inflation in count data regression. So I will first introduce a general test for the strictly non-nested models, which is called the Yik-Lun test. And then we will come to the topic whether the Yik-Lun test is appropriate for testing the zero inflation. And also I will introduce a score test for the zero inflated Poisson model. So the motivation here is to fit the count data. We have a lot of choices. One natural choice is the Poisson model. But if the data is over dispersed, we can use the extra Poisson, negative binomial model, or generalized Poisson model. But if the data is having excessive zeros in the data itself, we can use the zero inflated model or the hurdle model. So how to make a choice based on so many models? A natural way is to do some tests based on the data or based on your fit result of your model. And here, this figure is showing the frequently used models in the count data analysis framework. We can see this basic Poisson model is in the middle part of this figure, and we have the over dispersed model, negative binomial, and generalized Poisson on the 2 sides. And also, if the data is zero inflated, we can go downside. We will see the zero inflated models are at the bottom of this figure. And the M here indicates the testing for the over dispersed. So we will see the M is testing between the left and the right, but the omega, which is the test for the zero inflation, will be up and down. And my presentation is mainly focusing on the zero inflation test. So we will check the MB versus ZIMB or Poisson versus zero inflated Poisson and generalized Poisson versus ZIGP. Okay. So for test for zero inflation, first we will go back to the zero inflated structure of the model. It is actually a mixture of a constant zero and the original count model Fy. And we will introduce a gamma, which is the constant point mass at 0. We will want to increase the probability of being 0 for the outcomes. And we will have the density function of the original count model for y not equal to 0 part. And our aims here is to test the zero inflation by trying to find a more appropriate model between the 2 models to fit the data, such as we are testing between the zero inflated models versus their non-zero inflated analogs, like zero inflated Poisson versus Poisson or ZIMB versus MB. a commonly used test, Buon test. It is for the strictly non-nested models, and it has been used commonly for testing the zero inflation. And for this test, we have two specified models first, like F theta and G gamma, which have different parameter space. And this test is basically depending on the KL information criterion. And we use this identity to denote the KL divergence from the model to the true distribution H0. And one idea here is if a model has a smaller KL divergence from itself to the true distribution, then we will think that it is more likely to be fitting the data well. So based on this idea, the Buon test has the following hypothesis. The null hypothesis is we make the F and G is equivalently better good to fit the data because we have the same KL divergence from F to the true distribution and G to the true distribution. And for the alternate hypothesis, we have the F is better than G because we have a smaller KL divergence for F. And to estimate this identity, we have this consistent estimator. It is exactly the log likelihood function for model F, evaluating at the correspondingly pseudo maximum likelihood estimator. So based on this estimator, we can give the Buon statistic, which is also based on the likelihood ratio. And under the null hypothesis, we would have this Buon statistic tending to the standard normal. So one thing to note is to calculate the Buon statistic, we need to calculate two models. We need to fit two models, the F and the G, then we can calculate the log likelihood function here. And is the Buon test appropriate for testing the zero inflation? Actually, we know that the Buon test has been used for testing the zero inflation model versus its non-zero inflation analogs for many years, such as many papers or even the art packages are still using the Buon test to test the zero inflation. But it has been shown to be a misuse in this paper, Wilson at 2015, because the asymptotic distribution of the Buon statistic in equation 1 is actually based on the not strictly non-nested models. So what's the strictly non-nested models? The definition from the Buon paper is two models, F theta and G gamma, are strictly non-nested if and only if the two models have no intercept, which means we cannot adjust the parameters value to make the two models have the same density function or distribution. But if we look back to our question here, the zero inflation test here, we have the zero inflated count model and the original count model. We are actually only adding one parameter gamma to the original model, which means if we make gamma equal to 0, then we will have the zero inflated count model exactly the same to the original count model. So this means the two models we're testing here are actually nested. Then it is inappropriate to use the Buon test to test these two models. So here are two numerical cases to illustrate this argument. So the first case is we are generating the data using a Poisson distribution with one covariate. Well, we are fitting the data using two different models. One is the Poisson model, the other one is the zero inflated Poisson model. So this is equivalent to our question here, the zero inflation test. And we calculate the Buon statistic for like 1,000 times, and we show the simulated distribution of the statistic. You can see it is far away from the standard normal. And for the second case, we still generate the data using the Poisson distribution, but we are based on 4 covariates, X1 to X4. And we fit the data using 2 non-nested Poisson models. Like for the first model, we use the covariates X1 to X2. And for the second model, we use the covariates X3 to X4. Then the two models are non-nested. And we can check the Buon statistic distribution here. It is very close to the standard normal. So this result is showing that if we are testing two models which are actually nested, then the Buon statistic doesn't have a asymptotic standard normal distribution. So I will introduce this score test for the zero inflation test, which is a decent one for you to use. And it is specifically designed for the zero inflated Poisson model versus Poisson model. First, a recap of the zero inflated Poisson model. We just replace the original CAM models with this Poisson models as the function, and we still have this gamma as the point mass at zero we want to increase. So the null hypothesis for this score test is we want to test whether the gamma is equal to zero, and we use this ratio structure which is equivalent to gamma to zero, and we introduce these notations: the log likelihood function of the zero inflated model, and the score function, and facial information metrics. And then we can construct the score statistic under the null hypothesis, which is the classic sandwich structure of the score statistic. And under the null hypothesis, which is the theta equal to zero, we would have this statistic extending to the chi-square of degree of freedom 1. So one thing to note is, under the null hypothesis, we would have this theta equal to zero, which means gamma to zero, and we would have this distribution actually the original Poisson distribution. So this means we only need to fit one model to construct this score statistic. So summary for Buell statistic or for Buell test, it is based on the likelihood ratio, and this means we need to fit two models. And it has been commonly used for testing the zero inflation, but has been shown to be a misuse because the test is only for strictly non-nested models. And we also introduced the score test for zero inflated Poisson, and it only needs to fit one model, fit the simple Poisson model. And it can also be easily extended to other over-dispersed Poisson model like the zero inflated negative binomial versus negative binomial, or zero inflated generalized Poisson to generalized Poisson, which you can check the reference here. Thank you. This is my presentation.
Okay, so I just have one comment for this presentation. I think based on the description of the Von test, I don't think it's applicable to all the zero inflation issue we discussed in this class, because all the zero inflated model versus the non-zero inflated model we discussed in the class are nested, right? Poisson, zero inflated Poisson. So therefore, I think that assumption of non-nested models is clearly violated, so it's not applicable. And the score test, which we didn't cover in the class, you can check it out yourself. It's something very interesting. So like for the linear model testing case, we talk about the wall test, we talk about the likelihood ratio test, but we could also do the score test. It's also a very widely used type of test. And over here, so he talked about using the score test to test whether the zero inflation proportion is zero. But I actually have some skepticism about whether that chi-square distribution, chi-square 1 distribution holds. I think for the same reason we discussed for the likelihood ratio test in the class, that is when the parameter you test or the null value of the parameter is at the boundary of the parameter space, then there might be some issue with the asymptotics. And that chi-square 1 distribution for the score test is also asymptotic distribution. So I think that needs to be checked. So these are my comments. All right, so thank you everyone for your nice presentations today. I think we have seen a lot of wide variety of topics. So yeah, I think everyone must have learned something from your peers. So we will look forward to your report, which will be due in more than 1 week. And also I will appreciate that if you can fill out the evaluation form, online evaluation. I think it will be closed quite soon, probably by this Saturday, I think if I remember correctly. So if you could do that, we'll appreciate it a lot. Thank you. And if you have any further questions, you can let me know by email anytime. Thank you.
Thank you.
Thank you. And thanks, Dongyuan, for doing the screen sharing today.
Thank you.
Thank you.
And thank you for all your nice presentations today.
Thank you. Bye. Have a great spring break.